This video is on section 5.1, which is about area and distance. Up to this point in the class, we've been using derivatives to solve problems involving rates of change. And now we start essentially the second portion of our class, in which we address problems involving area and accumulation. To begin, we have this example where we want to approximate the area under the curve y equals x squared on the interval from 1 to 4 using 6 rectangles and right endpoints. So the first thing that we need to do is figure out what in the world we mean by these 6 rectangles and right endpoints. So the first thing we're going to do is we'll take our interval from 1 to 4 and we're going to split it up into 6 equal pieces. And those 6 equal pieces are going to form the bases of 6 rectangles. Now, to find the heights of the rectangles, this is where the endpoints come in. So in our first little piece in our interval, we go to the right endpoint of that piece, and then we go up to the curve, and we draw a rectangle of that height. And so we repeat that process. We go to the next interval, find the right endpoint, go up to the curve, draw a rectangle, and we're going to repeat that. Until we get a picture that looks like this. Now, we might not know the area under the curve y equals x squared because it sort of has this amorphous shape that we don't really know how to find the area of. But we can all find the area of a rectangle just by taking its base times its height. And so we're going to, our point of view is going to be to use rectangles like this to approximate areas that we don't know the value of. So here we're going to refer to this right-hand endpoint area estimation as R6. So the capital R is for right and the 6 is for the number of rectangles. And now we're just going to add up the areas of all of those rectangles. So our original interval, the interval from 1 to 4, is of length 3. And we broke that up into 6 pieces. And so what that means is that each piece, at least along the base, or each piece, has length of 1/2. So that 1/2 is the length of the base of each one of those rectangles. And then for the height, we have to go up to the curve. So our first right-hand endpoint lies at 1.5. And to get up to the curve from 1.5, I have to take that 1.5 and square it. And the reason I'm squaring is because I'm told that heights of points on the curve are found by squaring numbers. And then, so that, what I've just written down there is the area of the first rectangle. Then I go to the next endpoint, which is 2, and I look at that second rectangle. Its area is going to be 1/2, which is the length of the base, times 2 squared. And so I proceed in this fashion. And I keep going. And my very last rectangle has base 1/2, as they all have. And then the height of my very last rectangle, it's at x equals 4, and so I know to get the height of this piece right here, I need to square the value of x. And now if you pull out your calculator, you can compute this. In fact, you might want to factor the 1/2 out first, and then compute the sum of the squares. So it'd be 1/2, and then if you add all of those things together, you should get 49.75. And then dividing by 2, multiplying by half, gives you 24.875. And so we should interpret that number as being an approximation of the area under the curve, y equals x squared. And in fact, we know that it's going to be a little bit bigger than the actual area. So it's an upper estimate of the actual area because, as you can see, these rectangles sort of overhang the curve. And so we get some extra area here that we've built into our calculation that really doesn't occur under the curve y equals x squared. Now we can think about this computation physically, perhaps, in terms of a distance calculation. So for instance, let's suppose that the x-axis measures time. So say we're going from time t equals 1 second to time t equals 4 seconds. And if we think of the y-coordinate, for instance, as representing velocity, I don't know, perhaps in feet per second or something like that, then each one of these rectangles that we've computed, each area of this rectangle is a base times a height, which in terms of our new physical setting, that is where the horizontal axis is time and the vertical axis is velocity, what you're doing is you're taking a little bit of time, that's the 1/2 part on the horizontal axis, and you're multiplying it by some heights, which are velocities. And when you take a time times a velocity, what you wind up with is distance. And so when we make this calculation, this sum of areas of rectangles, we can think about this as an approximation of the distance traveled by some object over the course of 3 seconds, where the speed of the object is given by the square of the given time. So if you didn't like the last example, well, guess what? Here it is again. And it looks nearly identical, except this time instead of using right endpoints, we're going to use left endpoints. Okay, well, we have these 6 rectangles that we want to form. And just as before, we take our interval, which goes from 1 to 4, and we want to split that up into 6 equal pieces. So we do that, we've split our interval up into 6 equal pieces, and those pieces, each one of those pieces is going to form the base of a rectangle. And then the only question is, well, how do you form the height of the rectangle? Well, in each piece, like this first piece, instead of going and finding the right end point, we're going to find the left end point, and from there we'll draw a segment up to the curve, and that will allow us to form a rectangle. In the second piece, again, we find the left interval, or excuse me, the left end point, and then we go up to the curve until we hit the curve, and then draw a rectangle of that height that extends over that entire piece of the x-axis, and we just repeat this. At each interval, we find the left end point, we go up to the curve to form a rectangle. And so there we have these 6 rectangles. And now what we want to do to find the estimate of the area under y equals x squared is to add up the areas of all of those rectangles. So we'll denote that by L sub 6, where the capital L stands for left, as in left end point, and the 6 is the number of rectangles that we used. So each rectangle has base 1/2, and then the height, Well, that will depend on the rectangle. So this first rectangle here, the height of that rectangle is the left endpoint 1 squared. Now, y squared, well, remember, we are, for a given value of x, to get up to the curve, we have to square that value of x. Okay, now we move on to the next rectangle of base 1/2, and its left endpoint is at 1.5, and so the height of that second rectangle is 1.5 squared. And we continue to do that up until the sixth rectangle, which again is of base 1/2, and the height this time is 3.5 squared, and that's because the left endpoint of our final rectangle is at 3.5, and to get up to the curve we have to square 3.5. So if you add all of that stuff up, you should wind up with 17.375. And we note here that this is not exactly the area under y equals x squared. In fact, it's an underestimate because, as you can see, there are portions of the area under y equals x squared that were not accounted for in our computation. So the calculations that we made in the previous examples can be cast in more general terms. So here, what I want you to do, you'll see at the top that there are two pictures, and I want you to focus first on this picture on the right that discusses the right endpoint picture. So instead of y equals x squared, we might be starting with just y equals f of x for just some function, f of x. And instead of having 6 rectangles, we could have any number of rectangles. Let's say we have n rectangles. So we could take our interval. In this case, in the previous example, we had the interval from 1 to 4. Here, more generally, our interval could be from A to B. And we want to take that interval from A to B and we want to split it up into n pieces. So each piece is going to be of length delta x. Right? So those are the lengths of the pieces along the x-axis. And how big are those pieces? Well, in the last example, each one of those pieces was of size 1/2, which we obtained by taking the length of our interval, which was 4 minus 1, or 3, divided by the number of rectangles, which was 6. Here, the size of each piece is going to be the length of our interval, which is b minus a, divided by the number of rectangles, which is n. Okay, now if we want to form r sub n, which is the right-hand endpoint estimate of the area under the curve, we need to, as in the previous example, compute the sum of areas of some rectangles. Each rectangle is going to have a base delta x, and the height of each rectangle is going to be found by evaluating f at one of these x's that sits in this partition of the interval from A to B that we computed, or that we made by dividing the interval up into n pieces. So we have x1 and then x2 and then x3, and we keep going until we get to the right-hand endpoint b, right? Okay, so r sub n, this is our right-hand endpoint area estimate. It's the height of the first rectangle times its base, and then you take the height of the second rectangle times its base, and then finally you just keep doing that until you get the height of the last rectangle times the base. Now in these area approximations, there's a lot of adding going on. And so we introduce, in the second line here, we introduce the Greek letter sigma as an abbreviation for adding up a whole bunch of things. So this Greek sigma, you see on the bottom we have I equals 1 up to n. And the thing that occurs next to the sigma, what we're going to do is we're just going to keep adding those things. So the sigma means that we're going to add, and the extent of that addition is given by this notation I equals 1 to n. So that's what the second line means. Now the third line looks rather complicated, but it turns out it's absolutely necessary for us if we're going to be making computations in the future. So these x sub i's, what are they anyway? Well, like here in our picture, the right-hand endpoint picture, let's look at x sub 1, for instance. What is that? Well, how do I get to it? Well, I could start from A. And hop over 1 delta x to get over to x1. But what is delta x? Delta x is this b minus a over n. And so if I want to get to x1, I could start with a, and I could add on 1 copy of b minus a over n. On the other hand, if I wanted to get to x2, I could start with a, and I could hop over 2 copies of b minus a over n, and so on. And so to get to x sub I start at a, and I hop over I copies of b minus a over n. Okay, now what about this b minus a over n at the end? Well, remember, that's just delta x. So in this last equation, you can think about this as sort of this whole notation here in the last equation as being sort of an expanded version of f of x sub I times delta x. Okay, and here we have sort of the same story, except now we're going to talk about left-hand endpoints. So it's very nearly the same discussion that we just had. So we take our interval from A to B, and we're going to split this up into n pieces of equal length, and as before, that equal length is going to be the total length of the interval divided by your number of rectangles. So we take our interval, we divide it up into pieces of length delta x, and then we mark out little hash marks on the interval from between A and B that mark out these little pieces of length delta x. So we go from A to x1 to x2, etc., up until we get to B. And then what we want to do is form rectangles over each one of these little pieces by finding the left endpoint and then going up to the curve and drawing a rectangle. So as in the previous calculation, we're going to call that L sub n, and to form that, we just add up the areas of these little rectangles. So each base is of length delta x, and then the height is obtained by going to the left endpoint and applying f. So here, by the way, A is going to be regarded as x sub 0. Right, so notice our first rectangle involves an f of x sub 0 because that x sub 0 is the left endpoint of the first subinterval. Okay, so we keep doing that until we get down to the last rectangle, and the left endpoint of the last subinterval is going to be not x sub n, but x sub n minus 1. All right, so then again, as on the previous slide, we can abbreviate addition using the Greek letter sigma, except this time the values of I are going to run not from 1 to n, but rather from 0 to n minus 1. And then in the third equation, all we're doing is writing x sub I in terms of a, n, b, and I, just as we did on the previous slide, and delta x, as we mentioned a few moments ago, is b minus a over n. It's important to notice that if we increase the number of rectangles, that is, if we have a lot of skinny rectangles, then the approximation of the area that we get by adding up the areas of those rectangles is closer to the actual area under the curve than if we had just a few rectangles. So that is illustrated by this figure here that you see. We have this y equals f of x on an interval from a to b, and you can see that if we split that interval up into a bunch of little pieces, thereby forming a bunch of rectangles, the area that we form by adding up all those rectangles looks a lot, or looks very, very close to the area under that curve. So in particular, if you have a fairly well-behaved function, let's suppose f of x is continuous on the interval from a to b, then we could actually get the exact area under the curve, or the exact signed area. So I'll be talking a little bit more about what that means in a little while. But the exact area under the curve should be given by a limit as n goes to infinity of these rectangular area approximations, either ln or rn. Either one will work as n goes to infinity to give you the exact area under the curve. Okay, now instead of merely approximating the area under y equals x squared on the interval from 1 to 4, we're going to compute the area exactly using the formulas that were on the previous slide. So in particular, we're told that the area is limit as n goes to infinity of, say, the nth right-hand endpoint estimate of the area under the curve. So a moment ago, or a few minutes ago, we computed the value of R6. And now what we want to do is to imagine, well, what happens if we replace 6 rectangles by 12 rectangles, or 18, or 24, or some number of rectangles that's just getting larger and larger. Okay. Now, the nth right-hand endpoint estimate is a sum of areas of rectangles from I equals 1 to n. And we were told on the previous slide that we get that by taking f of a, which is our left endpoint. Well, in this case, our left endpoint is 1, plus, and then we take I times b minus a over n. Well, b is 4, and a is 1. 4 minus 1 is 3. So b minus a times I would be 3 times I divided by n. So that's the height of a little rectangle, and then the base is delta x, which is 4 minus 1, or 3 over n. Okay, so let's keep going on with this. Now you might be wondering, well, what is this f here that's right next to the Greek summation sign? What is that f? Well, in this case, the function is just the squaring function. That's how we get up to the curve. So let's write that part in. So this is the limit as n goes to infinity of the sum I equals 1 to n. And what are we doing with this input 1 plus 3i over n? Well, the function that we're applying to it is the squaring function. Okay, now this is the limit as n goes to infinity. And I see that I forgot to write the infinity over in the last expression, but there it is. So the limit as n goes to infinity of the sum I equals 1 to n. And now if you take this whole mess here, if you square the 1 plus 3i over n, that becomes 1 plus 6i over n plus 9i squared over n squared times 3 over n. And now let's see if we can simplify that down just a little bit more. So if we multiply through by 3 over n, we're going to get this. We'll get 3 over n plus 18i over n squared plus 27i squared over n cubed. All right, now that looks like one just big fat mess, right? And so the question is, what in the world do we do with that? How in the world can we take that mess and turn it into a number? And in order to do that, we need just a little bit more information. Okay, the computation on the previous slide involves adding up a bunch of things. So if we're going to finish that example, we need to learn a little something about how to add that we might not have known previously. So here on this slide, we have 3 formulas involving addition that are going to be used quite frequently in section 5.1 and section 5.2. So the first formula has to do with adding up the first n natural numbers. So if we start with 1 and then we add 2 and then we add 3 and so on and so forth up until we get to like n, it turns out that you can add all that together just by taking n times n plus 1 divided by 2. The second formula tells us how to add up a bunch of squares. So if I take 1 squared plus 2 squared up through n squared, add all that stuff up, apparently that can be done just by taking n times n plus 1 times 2n plus 1 divided by 6. And then the final formula here involves cubes. I take 1 cubed plus 2 cubed up through n cubed. That apparently is n times n plus 1 over 2, quantity squared. Now, it might be, we're not going to prove these results, but it's sort of fun just to check to see if they work in some special cases. For instance, this last formula, let's suppose we just take 1 cubed plus 2 cubed. Well, that's 1 plus 8. Which is 9, right? Well, let's see if that's given by this formula here, the n times n plus 1 over 2. Well, in this case, n is equal to 2, right? We're stopping with 2 cubed, so n is equal to 2. If I take 2 times 2 plus 1 divided by 2, and I square it, right? That's what That's what this formula here is telling me to do. Well, what do I get? Well, I get 1 times 3 squared, which again is 9. Okay, so when n equals 2, this bottom formula works. Now there is one more formula that I probably should have put on this slide, and I'll just give it to you now. And it's this one. Let's suppose we just add 1 to itself n times. So you can imagine this as just being 1 plus 1 plus 1 plus 1, and then you have n of these 1s. Well, if you've got n 1s, that's just the same as having n. Okay, so that formula also is useful going forward, and in fact we're going to use that formula in addition to some of these others to finish out the example that we had started on the previous slide. So now we're ready to finish the example we started a couple of slides ago using the formulas that we learned on the previous slide. So you might remember that the purpose of the example is to compute the area under y equals x squared on the interval from 1 to 4. And you might remember that a couple of slides ago we had wound up with this really sort of ugly looking limit to compute that involved this sort of gigantic sum of things. And that sum looked like this. So I'm going to call it S. And it was the sum I equals 1 to n, 3 over n plus 18 I over n squared plus 27 I squared over n cubed. Now we're going to try and simplify that expression or that sum using the formulas that we learned on the previous slide. So the first thing that we can do or try to do is to split this up into pieces. So remember, if we have a bunch of numbers, it doesn't matter what order we add them up in. So we could add the 3 over n's first, then the 18i over n squared second, then the 27i squared over n cubed third. And you might notice that these quantities 3 over n, 18 over n squared, those things don't have anything to do with I, and so we could factor them out in front of the sums. So we could write this actually as 3 over n times the sum I equals 1 to n of 1. So that's the first bit of the sum. And then plus 18 over n squared times the sum I equals 1 to n of I. And then finally 27 over n cubed times the sum I equals 1 to n of I squared. And now we're ready to use those formulas that we learned on the previous slide. Right, if we add up n ones, that's just the same as n. Right, that's the very last formula I discussed on the previous slide. And then the 18 over n squared doesn't change. But if I add up the first n natural numbers, 1 plus 2 plus 3 up through n, that is n times n plus 1 over 2. And then finally we get this 27 over n cubed, and then the sum of the first n squares, remember, was n times n plus 1 times 2n plus 1 all over 6. Now remember, when we were computing the this area, we wanted to find the limit as n goes to infinity of this whole mess, right? So we're taking the limit as n goes to infinity of s, this sum. Well, that's the limit as n goes to infinity of all of that stuff. And now that might seem rather ugly, but actually you're just looking at a limit of at infinity of some rational functions. And you learned how to do this back in chapter 2 somewhere. We learned how to take limits of at infinity of rational functions. The first bit as n goes to infinity is just 3. The second bit here, well, 2 goes into 18 9 times, and then the remaining limit goes to 1, so this becomes 9. And then the third one, the leading coefficient in the top polynomial is going to be a 2 times 27, which is 54, divided by 6, which is going to be another 9. So if we add those numbers together, we get 21. And that 21, in computing that 21, we've done something momentous, right? We have computed exactly, not just approximated, but exactly the area that is under this curve y equals x squared on the interval from 1 to 4. So in this last example, we're going to find the area between y equals x plus 1 and the x-axis on the interval from -2 to 2. So you might notice again, here we have this reference to signed area. And now is the time for me to tell you a little bit about by what's meant by signed area. So here, you might notice that on the interval from -2 to 2, part of the curve lies below the x-axis. And any portion of the area that occurs below the x-axis is going to be treated as negative. And so if I want to find the signed area between the curve and the x-axis, what I do is I take the area of all of the stuff that's above the x-axis. Let's say that's A1. And then I take the area of all the stuff that's below the x-axis. Let's say that's A2. Then the signed area, the thing that we seek, is A1 minus A2. Now the formulas that we saw earlier, in fact, that we employed to find the area under the curve y equals x squared, those formulas work to compute not just area, but signed area. Now we didn't see that on the previous example because the curve y equals x squared on the interval from 1 to 4 does not go below the x-axis. But if it had, the formulas that we employed would have given us the signed area between the curve and the x-axis. Okay, so here, we have some options. We're supposed to compute this signed area. One thing we could do is go back and, compute a limit of sums of areas of rectangles. And that would result in sort of a lengthy process, which we saw just in the previous slides. But the other thing we could do is just notice that this area can be computed through just by finding some areas of triangles, right? So there's no need to overcomplicate our lives when we can just use a little bit of geometry here. So you should do that unless you're instructed to do otherwise, right? So I know that A2, for instance, in this figure, how do I find the area of a triangle? Well, it's 1/2 base times height. So the base and the height in this case are both equal to 1. A1, on the other hand, again, is a triangle. Its area is 1/2 base times height, and its base and height in this case are both 3. So if I want A, which is the signed area, I take A2 minus A1, or excuse me, it's actually A1 minus A2, right? Because the stuff below the x-axis is to be treated as negative. And I get 9/2 minus 1/2, which is 4. So the area, the signed area anyway, between the curve and the x-axis is equal to 4. And we were able to obtain that in this special instance without having to take limits of sums of rectangular areas. We just used the formula for the area of a triangle.